Hey everybody, welcome back. It's Mr. G here again. What we're going to be doing today is the next in the lecture series for power electronics, which is focusing on lab number 6, which is on phase control. So, before we get into lab number 6, let's take a minute and look back on what we've learned from lab number 5. So, a couple of key things again. Conduction angle. So conduction angle is a measurement in degrees of the time that something is conducting. And in our case, it's the thyristor. So the thyristor we're using is an SCR. So it's the time in degrees relative to 360. So when you're measuring it on the scope, the time over x is equal to, here's the period of 360 degrees. And you solve for x and that will give you the angle. So again, on your scope, you're measuring time. So for an SCR, we're looking at a conduction angle that is slightly less than 180 degrees. In lab number 5, we looked at the shifting point trigger circuit, where we introduced a potentiometer. And what that did was, if we had a voltage here, example, a gate trigger voltage at 2 volts. So again, the 2 volts is when this device would turn on. So based upon a voltage divider, and the value at which Rx is, we can figure out where in the waveform we actually hit 2 volts on that gate. And then we can adjust the pot, which varies this part of the variable resistor, and we can actually adjust at which point along this waveform we actually achieve 2 volts at the gate to turn this on. So we can actually go all the way up to here, which reduces our conduction angle to a little bit less than 90. Or we can shift that point all the way down, somewhere down here, where we're back to slightly less than 180 degrees. So what we're doing, again, is we are shifting along this waveform via a voltage divider, which point along this waveform we actually achieve 2 volts at the gate in order to turn it on. So that is shifting point trigger, and what that does is it allows us to vary the conduction angle of this circuit. Alright, so lab 6 is on phase control. The goal again is to be able to control the conduction angle of a circuit. So in our case, the conduction angle of this SCR, therefore controlling the effective voltage that makes it to our light bulb. So phase control, we have a rheostat. We have a capacitor, that is our phase shift component. We have a diac, and we have SCR, our light bulb. And then we have this protective resistor. So if this value was zeroed out, we want to make sure that the gate circuit is not connected directly to the power supply. So even though we would zero out this rheostat, there's always going to be some resistance in line to limit the current down that circuit. So the rheostat does the adjusting for us. The capacitor is our phase shift. So we have a little RC circuit, so a variable RC circuit that allows us to vary an angle based on the effective Z, so the impedance. The diac is there to increase the amount of voltage that is required here to actually turn on the device. Remember, if we had like 2 volts as a gate trigger, by putting the diac here, we can now increase this, and we can actually have a larger value that needs to be put here to get this to conduct before the gate actually turns the device on. So what this component does is it's increasing the voltage that must be present to turn the SCR on. So X. And I'll talk about why in a minute. So, again, if we are going to put on a scope and monitor the waveform from anode to cathode. So the input is a typical sine wave. So the input on the sine wave. With the shifting point trigger, what we did is we adjusted a pot in order to pick a different spot along here based on the voltage divider of when the device gets turned on. But now, what we're doing is we're not shifting a voltage point, we are shifting a voltage waveform. So let me see if I can explain that for you. So I have a little waveform here, and this waveform represents the input waveform, just like we had in the shifting point trigger circuit. This X here is identified by this X here. So what that means is, in order to turn on the SCR, the voltage has to climb to this point. So the input voltage has to climb to this point in order to provide enough voltage here to get this to conduct. Remember from our early discussions on thyristors, we need a breakover voltage. So we got a breakover voltage plus our 2 volts. So whatever value X is in this circuit, let's say it's there. So the voltage has to climb to X in order to get this to conduct, trigger that gate, and get this to conduct. So if we take our waveform, So if we take our waveform and we apply that concept, if I was to take that point and move it up, what our waveform would look like across anode to cathode would be voltage is rising, hits that point, then we start to conduct, and then we turn off because we're falling below the holding current again, and we remain off. And then the whole thing repeats itself. So this is the voltage we're looking at that gate. So this waveform here, point X, that's when there's enough voltage to trigger the SCR and get to conduct. So if we looked at the voltage anode to cathode, it would be this black value here, or this dark gray. So where it triggers is where it turns on. So when we adjust our pot in this circuit, what we're actually doing is introducing with the pot and the capacitor, we are introducing a controllable phase shift. And that phase shift is between the applied voltage and the voltage that makes it down this gate circuit. So in this particular case, here's my applied voltage, the red. Okay, so the red is my applied. And the green is the waveform that makes it down the gate circuit. The way it sits right now, there is a 0-degree phase shift between the two. So basically the voltage V in and the voltage that makes it down the gate circuit, there is a 0-degree phase shift. Between those two waveforms. They are in phase. If I start moving this pot, I am introducing a phase shift based on that RC circuit. So what that means is this green waveform will start to shift with respect to the red one. So that means that this waveform will actually shift. How much will it shift? Well, the maximum amount of phase shift introduced by a capacitor is 90 degrees. So that means from this location here in phase, we can actually shift to approximately 90 degrees. So let me introduce that on another waveform. So here we are, we're in phase. I adjust the pot and the green waveform shifts. So we go from 0. So that means that this point and this point are the same point. and then I shift it to approximately 90 degrees. So now this point here is there. So by adjusting the pot, we are adjusting the phase angle of this waveform from approximately 0 degrees all the way up to the maximum you can get from a capacitor is 90 degrees. So we go from here, 0 degree phase shift, to 90 degree phase shift. Now, we're not actually changing the value at X in this circuit. The physical value of X is still there on the waveform. So that means at this point is where we turn on the SCR. So here, when we were in phase, when we were in phase, our turn on was here and our conduction angle was this. Now, if we take that and shift it 90 degrees, look where our point is where we turn on the device. So now, off, 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 and the device turns on. So, when we're not introducing any phase shift, the device turns on here, and we have a conduction angle of this. When we shift the waveform, we shift to here, and now the conduction angle is this. So remember, the conduction angle is measured at the flat part. So there's the conduction angle, and there's the conduction angle. So, what we've achieved is a conduction angle that's from here to here. And what I'm going to do is I'm just going to bring this up so we can look at it on one waveform. So we can adjust the turn-on point from here to here. Now, one thing you're going to notice that the range is larger in a phase control than it is in shifting point trigger. So that means from minimum to maximum has a larger range, adjustable range. Something else you're going to realize is here our minimum conduction angle is a lot less than the minimum in the shift point. So the shifting point, the minimum was 90 degrees. Here our minimum is much smaller. One of the other advantages of this system is in shifting point, let me do a second wave. In shifting point trigger, so this was the area we were controlling. So we went from 90 degrees. So if we turned on at this point, we went from 90 degrees approximately and slid up to wherever that was. So the minimum was 90. The maximum was approximately a little less than 180. So 180, approximate. Now your values, this is definitely going to be less than 180, and this will be a little bit less than 90, but hopefully you get the picture. Okay, now this is the point at which it turns on. That's the minimum value right here. In this one, the minimum value is here to about there. So remember, here, this is the conduction angle, and if I slid this point over here, this is the conduction angle. So now, I'm going all the way over here. This is the conduction angle, and I can adjust it all the way over here to this is the conduction angle. So this one has a larger range. Also, you can actually get smaller minimum conduction angle. So, using phase control, the point at which we turn on that waveform stays the same, so where X is, but what we're doing is shifting the whole waveform to trigger a new point. X remains the same in amplitude, but now what we're doing is we're shifting it in the time base. Whereas with shifting point control, we're actually shifting it in the voltage, so in amplitude. So, in conclusion, phase control typically has a wider range of conduction angle and a lower minimum conduction angle. So that means our light bulb, we can actually control the voltage going to the light bulb. So our light bulb will be able to go dimmer, 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 dimmer before it shuts off. Whereas with the shifting point trigger, it went dimmer, 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 shut off. So we can actually control a lower minimum conduction angle. So therefore we have better control of our overall effective voltage. So now, some people always ask, well, Mr. G, why don't we just control a light bulb with a potentiometer or something? Like this. The problem with this type of circuit is that it is very inefficient. Why? Because the current that is going to the load, so the current that's going through the load actually has to flow through part of that resistance, therefore creating power and loss of energy. In a circuit like this, the load current goes this way, and this is a very, very small control current. So the amount of current going through the resistor in this part of the circuit is much less than this would be. So therefore, this is a much more efficient way of controlling the effective voltage to a load. Well, I hope this helps. Again, this is power electronics, phase control for lab number 6. Until next time, everybody take care, stay safe.